hello to everybody.
20 minutes.
Okay, welcome everybody guests in the US. I represent the same lab, the same institution as Michael Yalandin before reporting. And also I would like to start my report from the beginning to make some, maybe some words about the name of the report. And now I think that it's better to say that it's not a subnanosecond breakdown, it's maybe pre-breakdown processes we are investigating, because for our pulses, in our case, we have no any subnanosecond breakdown in the presence of a strong axial magnetic field. And this work is the prolongation of our previous works. Everything is the same in this publication. You can see this publication was made in a collaboration with the Institute of High Current Electronics, the theoretician in the first line of the OSA, and everything is the same, but in the presence of the strong axial magnetic field only. So, but the aim of the talk is just to find fundamental limitations on the breakdown strengths of gas coaxial feeders. So, no need to speak because we have about the setup in general, because this part is the same as you have seen on the previous report. I just point your attention that tomorrow it will be the invited lecture of academic Shpak devoted to the 40 years anniversary of the radar systems. So that you can see how many various investigations we have made using these devices. Now I just fix your attention only at this part, because this is the maybe represents the line, coaxial line with 45 ohm impedance, and it was told already in the previous report. Then we are using reflectometry method for investigating the breakdown processes, and in this case the line impedance must be very uniformity, has very uniformity, and it was made, this line, with the uniformity up to plus minus 0.5 ohm from the beginning of the duct and to the close end of the line. So here you can see the voltages we are operating with due to the chopper of the spark gap technology on the slicer. You can easily adjust the time duration and the voltage amplitude of the investigation pulse. Here you can see the same current probe with station time about 20 picosecond, permitting you to observe the runaway flows electrons in the field of the breakdown area. Okay, so as you can see that the setup is very simple. It's just the line. It is the possibility to set the enhancer, electric field enhancer, in the cross-section of the current probe. The solenoids, two solenoids, makes it possible to set the magnetic field in the area of the enhancer up to 2.4 Tesla. And because it was, as it is very easy to change the amplitude and simultaneously the duration of the incoming pulse in the line, we can set, with the help of the current probe, we can set the runaway electrons on set or starting point at the right time of the pulse. And for our case, it's necessary to speak about the time duration starting from this point. And as you can see, for the highest pulse, it's about 150 kV and about 300 picosecond pulse durations at half amplitude. This time is about shorter, 200 picosecond. As the simulation in vacuum approximation showed that for such enhancer installed here, it's the minimum flight time of electron to the inlet is about 80 picosecond, and so it is comparable for this the time duration of our high voltage pulses coming in this in the line. And so simply our task was just to increase with the help of the magnetic field, with the rotation of the electrons, just to prolong this time and don't permit to have a breakdown in this of the line. Okay, on this slide you can see the first reflectometry traces from the scope. In this case we have no any enhancer in this sphere, and you can see the first window, it's the incoming pulse that coming in the line. The second window corresponds to the area of the breakdown, the area of the enhancer installed, and the third window is corresponding to the reflected pulses. Here I would like to pay your attention that this line, it was possible to make a vacuum inside, and the reflection, which is coming from the short circuit end of the line, has the maximum amplitude. It repeats the case of vacuum insulation. But you can see the difference in the incoming and the reflected pulses. It's due to the excitation of the waves of dispersive type in the line. And here you can see that for such a shorter time of 150 keV pulse, we have about 10% losses of the amplitude, and for the shorter pulse up to less than 200 picosecond pulse duration, these losses is about 20%. What else? Here you can see the reference on the scope. It is just a special metal diaphragm, metal disc was installed here just to show the place where the enhancer is installed, and to see it. This reference imitates the instant communication now in our case. So there's no field, no any enhancer on this slide. This is the case when we install the enhancer with such parameters, and the maximum electric field in this case is about 380 kV per centimeter. This field is slightly less than it is needed for start runaway electrons, because for our investigations and it was estimated that this field must be about 450 or 500 kV per centimeter to start the electrons from the enhancer region. And what we can see here, with the absence of the magnetic field, we can see that the reflection from the end is less essentially as it was previously without an enhancer. But when we switch the field at some level, we restore the amplitude of the reflection here. But at the same time, we can see that there's no any reflections in this area at all. I just want to point your attention about the stability of the pulses, that these traces are the accumulation of 10 pulses, and you can see that the stability of the incoming pulse and the reflections and the stability of the noise in the area of the enhancer is very stable. Okay. The most interesting case when we set the next enhancer with such parameters which guarantee the maximum electric field in this volume up to 1 megavolt per centimeter, and just immediately we can see the appearance of the reflections from this region, the region of the breakdown, possible breakdown. So the red trace corresponds to the zero magnetic field. When we increase the magnetic field, you can see that the reflections is become less than. So when we decrease the voltage up to only 20 kV only, but point your attention that there's decrease in voltage, but in time we decrease the pulse in about 1.5 times. So the time parameter is more essential here. So we find the mode when it was at the red one, it corresponds to the field, magnetic field number 0, And when we switch the maximum magnetic field for our case, we evacuate any reflections from the field of enhancer. And here on this basis you can see also with the absence of magnetic field, you can see the current from probe. The duration of electrons in this current is about 40 picosecond. Okay. If you know the incoming and the reflections, amplitudes and the signals, you can recalculate this window into the discharge current. But the physical sense of these currents are different. The curve number 1 corresponds to a short circuiting with the help of the metal diaphragm. The second curve is with a zero magnetic field, and the curve 3, 4 can be maybe assumed as the incomplete discharge current at different magnetic fields volumes. So the main maybe discussion questions: why, for example, in contrast with the vacuum mode, we have such high reflections from the region of the enhancer? From our point of view, the first one is because the orbits of magnetized electrons will be increased in gas due to a higher rate of energy gain in the front of the ionization wave, and pushing the electric field from the enhancer to the anode. In addition, the collisions with molecules starts to have an effect of drift effect and for runaway electrons, and according to our theoreticians, the time interval of high voltage at the level of 200 picosecond leads to about 3 millimeter drift, and together with the length, the height of the enhancer, it will be can be about half of the gap we are investigating. And the second maybe the third disadvantage is that because the reflection and the area of the investigated area stands about the large time interval, about 2 nanoseconds, the photoionization can play a significant role in the presence of plasma during the passage of the reflection. And here is my summary. So we can see that due to the rotational motion of plasma electrons and applied magnetic field, the gas region of ionized doesn't reach the anode and represent a reflected plasma layer. This layer can be reviewed as a discrete reflection line in gamma-hand. And the observed reflections just explained by changes in the volume of this ionization region, as well as the dissipation of term voltage wave energy in the plasma of incomplete discharge. So the larger field leads to a smaller radial size of the layer, but at the same time the intensity of the ionization increases with the increase of the magnetic field because the impact ionization cross-section increases. Thank you very much.
Questions, please?
Thank you very much. Have you considered side effects? Your configuration implied that the field crosses the tube, in fact, from both sides, from left and right. So electron could pass along the field and fall to the wall. Have you considered some this effect?
So what do you mean that?
Previous slide with the field with coils.
Okay.
This one. So this is. In this configuration, it's similar. Yeah, it's similar to mirror device, but in fact, this small mirror between the coils.
Yeah.
Side effects with field, the divergent field that crosses the wall. So electrons could move not across the field, but on the field.
Sure, it's so some maybe mirror effect is also present here, but we have the aim not to investigate this process, but we have the aim to increase the strength of the feeders. So we are not we're just looking for maybe the most purpose of the work is to show how to increase just without any enhancer the strength of the just line, the feeder. So this enhancer is just to show the role of runaway electrons in the speed of the development of this process only.
More questions? No questions? Please.
Thank you for an interesting presentation. You have mentioned that you use time domain reflectometry, also as Mikhail Yalandin mentioned. And he mentioned that it is a two-sensor reflectometry with two voltage dividers. Could you please explain, in principle, how does that work?
Okay, the main maybe feature. Oh, sorry. Okay. So the main feature for if you have the diode, for example, here is the same as it was for in the previous report. If the divider standing near the diode, the cathode, and it's necessary to use two dividers just to with the electrical length between them. This length depends. Because you have it's better to explain this one. If you have a long pulse, it will be a reflection from the diode, and to have the reflection more exact, more accurate to estimate its amplitude, you need to set two dividers just to make a special maybe calculations on the scope of this screen, just to shift the reflection from the closer capacitive divider to the one, and then make the mathematics to obtain the real reflection without any traces going after the. So it's. But in our case, we just use the one because we have a short times, and these times come from here to here without any additional reflections.
More questions? Thank you very much.